ladies and gentlemen, good morning. It's a great pleasure for me to be here today. So let me start going back in time, actually, and we are in the early 90s. And back then, the only planets we knew were the planets around our own star, the Sun. And you can see our Earth is down here, is one of the rocky planets with Venus and Mars and Mercury. And then this big planet here is Jupiter, 300 times the mass of the Earth, Saturn, 100 times the mass of the Earth. And then we have the icy giants, Uranus and Neptune, that are about 15 times the mass of the Earth. This is what we knew in the 90s. But then, actually, what we have discovered in the past 20 years or so is that, on average, every star in our galaxy is expected to have at least one planet in orbit, which is incredible because we're talking about billions of stars in our own galaxy, the Milky Way alone. And our galaxy is one of the billions of galaxies in the universe. So you do the math and you understand how many planets are probably out there. I'm afraid we don't know yet these billions of planets, but our counting for the moment in the past 20 years is about 4,000 extrasolar planets. So we're talking about extrasolar planets, meaning planets orbiting our stars, not our own sun, different stars, the stars that you see in the sky at night. Most of the stars do have planets in orbit. And so what is also quite extraordinary, in this graph here, you have the year of discovery, and now we're here. And you see from the 90s, really the number of planets discovered have increased exponentially, and it keeps growing. Now, we don't know so much yet about most of these planets that we have discovered. For many of them, we know the dimension, the size, how big they are. So if they are as big as Jupiter or smaller, like the other planets in the solar system. We know for many of them the mass, so how much they weigh. And from the fact that we know how far they are from their own star, we can estimate the temperature at the surface, if there is a surface of those planets, because the star is clearly the source of energy, and so the closer you are to the star, the hotter you are, the far away you are, the colder you are. So we still don't know too much, but even with those very basic parameters, we're seeing an incredible diversity of planets in the galaxy. Many of those planets do not resemble at all the planets that we have in our own solar system. And in particular, we have discovered that the most common planets out there are these planets that we call super-Earths, which are planets with the mass in between the mass of the Earth and the mass of Neptune, and probably some sort of hybrid planets we don't know too much about. But to show you how much diversity we're expecting, I'm going to show you a few science fiction movie images. And let me start with this one. Who has seen the movie Interstellar here? Yeah, many of you. So clearly you might remember this image about the water world. And actually we're expecting that many of the super-Earths might resemble this water world here because the density is suggestive of an interior that is probably made of ice, and the temperature might suggest that most of this ice is actually molten at the surface, so probably with some oceans. These Kepler 22b planets could be an example of water world. Again, from Interstellar, you might remember this small frozen planet. Most of the planets that have been discovered through the technique of microlensing are very, very far away from the star, and so they're very cold, and so presumably they might look like this particular planet here. Again, from science fiction, from the movie Star Wars, you might remember these lava worlds. We know today that there are many of the super-Earths that are orbiting so close to the star that they basically complete one entire orbit, in some cases, in less than 1 day. So can you imagine, for the Earth to complete one orbit around the Sun is 365 days, roughly. So here, to complete an orbit in less than 1 day, you're literally close to the star. And so the temperature at the surface for this planet goes beyond 2,000 degrees. So it's incredibly hot, and the surface that is probably made of rock is molten. And so that's why we're calling them lava worlds. And so this Corot 7b, for instance, is one of the examples that I have in mind. Again, from Star Wars, you might remember these planets that are orbiting around binary stars. And so planets for which you have 2 sunsets, 2 dawns, which is quite incredible and exotic to think about it. Now, we know, thanks to the Kepler mission, the NASA Kepler mission that was launched in 2009, that there is a long list of planets around these binary stars. We call them circumbinary planets. And so again, it's no longer really science fiction, it's reality. And again, this is the last slide about the connection with science fiction. But of course, you might remember the movie Avatar and the fact that in the movie there was this very interesting exomoon. Now, the hunt for exomoon is ongoing, and there is already an exomoon candidate since last year. So clearly, we're looking forward to see many more moons in the future. Okay, back to real science. I told you that we already know 4,000 planets, and they're very diverse. But actually, it will be in the next decade that we can really make a leap in our understanding of all these planets. To start with, we have a series of space missions that are already either flying or about to be launched by NASA and the European Space Mission that will deliver even more planets in the next decade. And so, in particular, there is the NASA TESS mission that is already flying, or the European Space Agency Gaia mission, and both of them are expected to deliver thousands of new extrasolar planets. And the Kio space mission is about to be launched by ESA, and later into the future, the Plato mission in 2026, again, will deliver even more planets. But of course, we also want to understand not just about how many planets we have in the galaxy, we also want to understand their nature. And in particular, today, I will talk about a few of the mission observatories that will be launched very soon in order to understand many of the characteristics of these planets. And in particular, we'll talk a little bit about Ariel and about the James Webb Space Telescope. So I was mentioning that we really want to try to understand the nature of these planets. And we have a series of questions that we want to be able to address in the next decade as scientists, but also as human beings, because ultimately we're all interested in this. And in particular, we want to understand what our exoplanet made of, what is the bulk composition, what kind of chemistry is there, but also what's the weather like there, what's the climate, how these planets are forming, why we're seeing all this big diversity in the galaxy that we're not necessarily seeing in our own solar system. And ultimately, of course, we're also interested about habitability, understanding whether some of these planets are habitable or not. So far, we have been able, at least for a few tens of planets, which are very big as our own Jupiter, to find out some of the most abundant molecules that are present in their atmosphere. And in particular, we are focused on giant planets as big as Jupiter, and these planets are mainly made of molecular hydrogen. But then what we have found out with current space telescope, in particular like Spitzer and the Hubble Space Telescope, that most of these planets do contain, for instance, water vapor in their atmosphere. And so for the moment, we know that water vapor is present for a few tens of these planets. And of course, we want to understand better these planets and understand whether there are other molecules, a more complex chemistry. But I also want to understand also smaller planets and colder ones, so get to the regime of the super Earth. And with current instrumentation, it's very difficult. We have a few observations, but are not really very conclusive. And so we really need to wait for the next generation. And talking about the next generation, the Ariel space mission has been selected by the European Space Agency last year to be the next medium-sized mission to be launched in 2028. I'm the principal investigator of Ariel, so I'm very, very happy that Ariel is going to happen. What is Ariel? Ariel is a 1-meter telescope that will be sent in a location called L2, which is 1.5 million kilometers away from the Earth. So here you have the Sun, here you have the Earth, and L2 is here. And from that position, we will look at the atmospheric composition and structure of about 1,000 extrasolar planets. And so we will try to understand what is the nature of this planet, what is the chemistry, what is the temperature, and really find out about what's going on in those faraway planets. Ariel will be built by a consortium of 17 countries that are part of ESA, and a NASA contribution is under study. And it will be integrated, tested and very high here in the UK, in the Harwell campus in Didcot at RAL Spaces. So we are very fortunate that we'll see basically this instrumentation coming up, being assembled here and verified here. If you're interested more in habitable worlds, then probably the first opportunity we'll have is to look at small planets, rocky type, around a very cold star. And the reason why we want to focus initially in those one is because, well, first of all, cold stars are much more numerous in our solar neighborhood. But on top of that, typically planets, since the star is colder, the planet that we are discovering right now are also relatively cold, and since they're cold and so close to the star, they are also easier to observe. And so in a few years' time, there is this big observatory called the James Webb Space Mission that will be launched by a collaboration between NASA and ESA. And James Webb will be able to look at the atmosphere of these smaller and colder planets. And so potentially this is our first opportunity to look at habitable worlds in just a few years' time. We're talking about not the twin of the Earth, we're talking about the cousins, but of course it's very, very exciting to start to see planets which are more similar to ours. And in the meantime, here in London, we're also working at the design and construction of a small satellite that is called Twinkle. And the plan is to launch Twinkle, which is as big as a dishwasher, more or less. It will be launched in low orbit. The plan is to do that in 2022. We're working with Airbus and our space industry in order to make sure that this is happening. And among many things, Twinkle will be able to look at exosolar planets, in particular the most favorable one, and start to tell us about their nature. And if you want to know more, again, this is an address of YouTube where you can see what the mission is able to do. So if you're interested in participating in this great adventure, there is plenty of opportunity for anybody at any age. And in particular, we have many educational programs connecting to many of these missions. One program that is currently extremely successful is called Orbits, and basically is coupling high school students in the area of London with PhD students from the University of London to do original research. And we have already a number of science papers that have been published in peer-reviewed journals as part of this program, which is extremely successful. So Orbits is clearly something that is growing and is going very well. But if you're interested in machine learning or AI, which clearly are very trendy words in the current society, both from a professional but also amateur way, we have some data challenges. The area data challenges that are available, anybody can participate to that. And we have at the moment 100 groups that are participating to this competition. The competition will be closed in mid-August, and the winners will be able to go to the European Conference on Machine Learning. So again, it's another opportunity where anybody really can participate. And finally, if you're interested in observations, if you have a telescope in your backyard and you like to look at stars, then of course you can help us, in particular to find the very best planets to look at for Ariel. We need to select 1,000 planets in 10 years' time, among the many that will be discovered at that point. And we need the help of everybody to keep monitoring the star and the planet through time and understand a little bit better the characteristic of the star, the position of the planet. And again, amateur astronomers will have the possibility of understanding through our website what are the targets that are visible in that week, in that month, in that year, and really help us with this program. I believe my time is about to be over, so let me wrap up to conclusion here. What we have learned in the past 20 years is that on average, every star in our galaxy has a planet, which is incredible because it means we're expecting billions of planets in our own universe. And we have all these questions that we really want to try to understand as scientists and human beings. What are they made of? What's their nature? What's the weather? What's the climate there? How they form? Why they're so diverse? Are they habitable? And my conclusion is stay tuned because the adventures are really just started. Thank you very much.
We do have some time for questions for Professor Tinetti.
In terms of the habitability question, how important is the magnetic field and the Van Allen belt kind of thing as part of that decision?
It's a great question. Of course, on Earth, we are lucky because there is a magnetic field that is protecting us from the radiation from the star and is also helping us retaining an atmosphere through time. And so we believe the magnetic field is very important. But so far has been very hard, actually, to measure directly the magnetic field of all these planets. And so it might need to wait a few more years where big missions like Athena or service from the ground like SKA will be online, and possibly some of those measurements will help us understanding whether there is a magnetic field or not. Today we still don't know about most of this planet what is the situation with the magnetic field. But you're right, it's such an element that needs to be considered.
Thank you.
You were talking about your focus on planets around stars which have got lower temperatures. When you're talking about that, is our sun a lower temperature star, or where does it sit in that spectrum?
That's a very good question. Our sun is a sort of an average, and so we're talking about a temperature for the sun around 5,800 Kelvin. Most of the stars I was referring to as relatively cold stars, typically around 3,000 Kelvin or so. So we're talking about stars which are much cooler and smaller compared to our own sun. But they have some disadvantages, and one disadvantage is they're very active, and so in particular, it's connected to the other question. Of course, if they're so active, you don't want to have all these flares coming from the star on your planet if you want to look at life. On the other hand, they're very common, the stars, and they also have a very long life, and so in that sense, they can provide perhaps a good host to have planets around them. The bigger is the star, the more unstable it is.
Because when you use a telescope, it isn't accurate, because if you go really far, because there's light years, you'll just see planet in the past or the future, in the past usually. Will that same effect be sent by the missions to space when they send it back, but instead you'll see the planet by the future? And then will it be accurate? Because obviously, if there was a water planet, then the water planet, if there was just a young sun, then the water planet would be able to have water. But when the sun grows older, the water would evaporate before it was sitting around, and it wouldn't be habitable anymore.
That's absolutely great question. Can we hire you in 10 years' time to help us with the mission? It's absolutely great question. And you're absolutely right that the far away you go, and then in a certain sense, you're traveling in space and time. But actually, most of the planets that we're discovering at the moment are still relatively close to us. We're talking about tens or hundreds of light years away, which is really nothing in cosmological sort of time. And so in a certain sense, although when we're looking at the light of this planet, you're right, that in a certain sense we're looking at these planets 10 years ago or 100 years ago, still is so close by that in a certain sense we're not too worried about that. So we are not able yet to look at galaxies and planets that are so far away that at that point the time question is important. But it's an absolutely great question.
Thank you. Time for one more?
Are there any planets with a similar atmosphere to Earth?
For the moment, we're not yet able really to sound the planets which are similar to the Earth, in part because if the planet is small and cold, it's much more difficult to look at the atmosphere. And so for the moment, we were able to do some super-Earths, but these super-Earths are very hot. In particular, 155 Cancri is orbiting very close to the star, is one of these lava planets. So we need to have more powerful telescope, and that's why we need this new generation in order to look at smaller and colder planets, because current telescopes are really not good enough.
Do you think there can be life forms on colder or hotter planets?
Yeah, I think we need to be very open-minded here, and so that's why I'm very curious to see about these planets around the colder star, their own sun. As I said, they're not the Earth twin, they're our cousin. But I think we need to be open-minded about life. Looking for a twin of the Earth is interesting, but maybe it's not the only type of planet that can host life. And so I think we need to be a bit open-minded and try to understand what's going on out there, given the diversity we are seeing. And so it's really just the first step that we're doing. But yes, it's a great suggestion. I would definitely look for planets which are not exactly like our Earth, but slightly colder, slightly hotter, slightly different, and we'll see what we'll find out.
Okay, thank you. Thank you very much. Enjoy the rest of your time at the Summer Science Exhibition.
Thank you very much.